Alright, thanks for watching. And today I want to present to you one of my favorite math theorems called the Banach fixed point theorem. And this theorem is super useful, namely, for example, to show that ODEs have a unique solution under certain conditions. And I will do it in generality, so let XD be a non-empty complete metric space, like this theorem. So let XD be a non-empty complete metric space and suppose you have some function from that sends x to itself and t from x to x be a contraction. Suppose t is a contraction. What this means is that if you start with 2 points x and y and you apply t to it, those points get closer and closer. So the idea is this: you have x and y, you apply t to it, and then t of x and t of y are closer than x and y. So this distance is always smaller than this distance by a certain proportion. So there exists a q greater than 0 and strictly less than 1 such that the distance of t of x, t of y is always less or equal to q times the distance of x and y. So it's very important. It's not necessarily true if q is 1. So just because t, makes distances not bigger, it doesn't mean it's a contraction. Then t has to have a unique fixed point. Has a unique fixed point. Point x star, that is t of x star equals to x star. In other words, if t is contracting, it means that at some point it crosses the line y equals to x, at least in the real number case. So t, you can think of it like this, or t of x star equals to x star. Horrible picture, but yeah. Okay, and in fact, it turns out it's an easy way, at least with an algorithm, to construct that fixed point. Namely, so in fact, the way you do this, suppose you start with an arbitrary point x naught, so any point works actually, and you apply t n times. If you take the limit of this, so imagine, I'm sure you've done this in a calculator, but you had a number, you press answer many, many times. Well, if your operation is a contraction, then in fact, after a while, the answer doesn't change. So you do get the fixed point by just starting with an arbitrary number and going up to, infinitely many times, pressing answer infinitely many times. And it's a cool theorem, but I really like it because the proof is very nice. It uses a lot of analysis. It's also one of those theorems where you need all the assumptions. But before that, since we're talking about metric spaces, let me tell you my favorite metric space joke. What do you call the distance between 2 points A and B? Bam. Okay. Enough fun, even though math is fun. So, proof. Let x not be arbitrary. And define xn recursively by, okay, so x naught is x naught, x1 is t of the previous one, t of x naught, x2 is t of x1, dot, 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 and then xn is t of xn minus 1. So xn is always t of the previous thing. It's the same thing as just pressing answer, every time. Okay, so first of all, I want to show you that if you take successive points, xn plus 1 and xn, they get closer and closer together. Namely, lemma 1, I want to show that dxn plus 1, xn, is less than or equal to q to the n dx1 x 0. Where again, q was defined by the contraction. So t of x, t of y is always q times better than x and y. So again, this just means every iteration we get a better thing, which should sort of imply that somehow they converge. So, proof. To prove this, well, it has to depend on n, so it's a nice induction argument. Well, base case, for n equals to 0, the proof is pretty trivial. So x1, x0, is this less or equal to q to the 0, dx1, dx0? Well, yes, because q of 0 is 1, and so we do get x1, x0 is less or equal to the distance of x1, x0. All right, now for the recursive inductive step, suppose we do have an improvement. Let's show we have a better improvement. So suppose dxn plus 1 xn is less or equal to q to the n dx1 x0. Well, let's see what happens with the next point. Then d xn plus 2 xn plus 1. So again, it's n plus, we replace n with n plus 1. But now, let's use a definition of t. Well, xn plus 2 is t applied to the previous term, which is xn plus 1, and xn plus 1 is t applied to xn. That's just the definition of t. But that's great, because we have the distance of t of 2 points. So now we can use the fact that t is a contraction. So this is less or equal to q times d of xn plus 1 xn. That's by contraction. And now we can just use the inductive hypothesis. So you see how cute this is? So that's less or equal to q to the n, dx1, x0. Again, that's an inductive hypothesis. And that's precisely q to the n plus 1. dx1, x0. You see, it's the same statement, but with n plus 1 instead of n. So that's good. So indeed, by applying t, we get closer and closer numbers. And in fact, first of all, it doesn't necessarily mean it converges, but we'll show that in fact they're Cauchy. Namely, voulez-vous Cauchy avec moi? Okay. Lemma 2, I got this from YouTube anyway. In fact, let's show xn is Cauchy in x. In other words, the terms xn, they get closer and closer together. Think of like people mingling, together, and it's a little party. And we want to show that, in fact, for large n, we do get that the terms are closer and closer to each other. And in particular, suppose, again, we want to compare xm and xn. So without loss of generality, suppose m is bigger than n. Again, we have like, this is xn, and this is xm. And let's find d of xn, xn. Or I guess xm, xn. And look, what does lemma 1 tell us? It tells us that at every step, we get a better and better estimate. So this is pretty close, this is even closer, and what we want to do is just separate it out into step by step by step. So, by the triangle inequality, we know that the distance here is just d of xm minus 1 plus d of xm minus 1 xm minus 2 all the way up to dxn plus 1 xn. So we sort of did it in reverse. We split up the distance between this little distance, this one, this one, this one, up to xn plus 1. And now we want to use our previous result. So what do we know? We know that this is less than or equal, so this is my lemma 1. So it's less than or equal to a q to the m minus 1 dx1 x0. Let me just double check. Yes, it's always this exponent. So q to the m minus 1 of that plus q to the m minus 2 of that plus that plus q to the n of that x1, x0. And the nice thing is you can factor out the dx1, x0. But not only that, remember m is bigger than n, so you can also factor out q to the n, and you're left with q to the n d of x1, x0 times 1 plus q plus q squared plus dot 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 up to, I guess, q to the m minus n minus 1. And look, this is the beginning of a geometric series, so the finite sum is less than or equal to the whole series. So this is less than or equal to qn d of x1, x0, 1 plus q squared plus dot dot dot. And by the sum of the geometric series, this has an explicit expression. So this becomes qn times 1 over q, 1 minus q, d of x1, x0. And what we want to show now is that this is small. So what we've shown really is that the distance between two, so dxm xn, is less than or equal to that. And now let's just use a epsilon delta argument to show that it's Cauchy. So now let epsilon be arbitrary. Let's taking it as a given that the limit n goes to infinity of qn over 1 minus q equals to 0. Again, standard calculus fact. Because this limit is 0, well, by epsilon delta definition, we know that there exists an n naught such that if n is greater than n naught, qn over 1 minus q, well, less than epsilon, but just to make it very elegant at the end, let's divide it by d of x1 minus x naught, epsilon over d of x1 minus x naught. So if m and n are greater or equal to 0, and with our loss of generality, m is bigger than n, we get that, again, dxm xn is less than or equal to this, but this is less than epsilon over d of x1 x naught, d of x1 x naught. That cancels out and we get epsilon. So in fact, we've just shown that the sequence xn is Cauchy, and very important, just because if it's Cauchy doesn't mean that it converges. I'm sure you've seen this sometimes in your life where you see just people grouping around and you think there's something, and sometimes there's nothing. That's an example where a Cauchy sequence doesn't converge. So, but there's one thing that we didn't use yet, namely completeness. So xn is Cauchy. So xn converges to some x star for some x star in x because of completeness. X is complete. Completeness means every Cauchy sequence converges. So if you see people grouping around, there is something happening. Okay, great. So the nice thing, by the way, about sequences and convergence is it gives us candidates for limits. That's why we care so much about subsequences and stuff. But we have this thing, and maybe this is a candidate for a fixed point. And in fact it is. So lemma 3 star, no, x star is a fixed point. And for this, just use the definition of t. So xn is t of xn minus 1. Now let's just take the limit. Again, before it didn't really make sense, but now we know that xn converges, so we get, I don't want to use this commutative diagram, so let's take the limit as n goes to infinity of xn, that equals to the limit as n goes to infinity of t of xn minus 1. But xn converges, so we have x star. Now, we want to put this limit inside, and in fact we can because of continuity. Xn minus 1. Again, t is continuous. Now, first of all, again, that's why continuity is so important. It's the stuff that allows us to put things inside, limits inside a function. And why is it continuous? Because of this contraction property. It's less than or equal to q of d of xy. And I'm not going to show this now, but it almost screams continuity. If epsilon is given, let delta be epsilon over q. Then, if this is less than delta, t of x, txy, their distance is less than q times epsilon over q, which is epsilon. So contractions are continuous. And in particular, we get that x star is t of x star. So in fact, x star is a fixed point. How cool is that? And in fact, I don't know if I mentioned this, but not only is it a fixed point, it's a unique fixed point. So I think if q is 1, I don't want to say nonsense, but I think if q is 1, then no, you might not still not have a fixed point, because we needed the fact that q to the n over 1 minus q goes to 0. So I believe they're counterexamples. So just lemma 4, in fact, uniqueness. It's very cute, you'll see. Suppose x different from y are fixed points. Then by fixed point definition, t of x is x, t of y is y. And now let's use the DAB definition, so the contraction definition. So d of t of x, t of y is less than or equal to q of t dxy. What? T of x equals to x, t of y equals to y. So we get d of xy is less than or equal to q, d of xy. But remember, q was less than 1. So we get that d of xy is strictly less than d of xy. And this is a big no-no. So it's a contradiction with the fact that there are two fixed points at least. So there can only be one. There can't just be one. It sounds like a 300 movie or something. Anyway, I hope you like this little analysis excursion. If you want to see more math, please make sure to subscribe to my channel. Thank you very much.